Good morning. Welcome to the Fluxion webinar this morning regarding the IonFlux automated patch clamp system. This morning's webinar will be primarily focused on the software interface, which we believe is intuitive and easy to use in controlling the IonFlux system. I was going to highlight several of the features, and in today's webinar, we'll be actually looking at the software in real time, although I don't have a system here that's actually running an experiment, so some of those details will be presented but not actually seen. But I do want to take you through the software and how we control it. To start with, I was going to do an overview of the IonFlux automated patch clamp system so that you can understand the control of the system in the context of the experiments that will be run. And just a few orders of business. If you have any questions during the course of the presentation, you'll see a chat window off to your right, so go ahead and please type in the questions. At the end of the webinar, we'll get to as many questions as possible. If we don't get to all of them, we'll respond by email. Again, welcome. So the IonFlux automated patch clamp system is the latest offering in the automated patch clamp field, which has been around for nearly a decade now. The IonFlux, we believe, represents the best in class for the technology as the latest runner in this field. We've brought the innovation of microfluidic devices to the automated patch clamp process. And that allows the reader to be a much more compact and simpler to use instrument. We produce very high quality data in the single cell configuration. We have gigaseal recordings. We also, due to the flexibility, also have an ensemble recording condition, which allows for higher success rates. Due to the fact that we have a microfluidic design, the system is cost effective and allows for a number of parallel recordings at the same time. We have two versions of the IonFlux, the IonFlux 16, which is doing 16 simultaneous recordings and operates in a standard SBS 9612 format, and then the IonFlux HT, which is making 64 parallel recordings, and the plate has a standard SBS 384 well footprint. The system is simple to use, and again, the focus today will be walking through those steps in the operation to get a feel for what it's like to control the system. So, so not only do we have a much smaller instrument and then much more of a plate reader type look and feel, but we've been looking to achieve the same within our software interface. And again, due to the fact that the system is much more compact and simple, and the fact that we are using microfluidic devices means that the liquids for the experiment are preloaded in before it goes into the reader itself, which makes for a much more compact and streamlined reader, and so therefore there are no robotics required. Although since it does operate like a plate reader, it is fully integratable with standard liquid handling robotics. And essentially within the instrument, there are only two moving parts. As I mentioned, we do have both an ensemble and single cell recording configuration, and these are shown down on the bottom. In the ensemble, we are making a single measurement across an ensemble of 20 cells, shown here, with each cell being at the end of one of these conical shaped, essentially equivalent to the pipette, with the reference electrode out in the bath, and then the recording electrode internally within what we refer to as a trap, which is the equivalent of the patch pipette. And then in the single cell configuration, it looks much more like a standard patch pipette, where we come down and we have a single cell that's being measured. And then there are two of these in each experimental pattern. And I'll go through the design of the experimental pattern so that as we start to walk through the software, you can understand what's being controlled. And one of the beauties of the system and the fact that this is in the plate design is that each of these consumables, whether it's a single cell configuration or the ensemble configuration, is used in the same instrument. So the IonFlux well plate from the top looks like a standard SBS format plate. It looks like a 96 well plate for the IonFlux 16 or a 384 well plate for the IonFlux HT. What makes these different is the fact that we have microfluidic devices on the bottom. And so each experimental pattern occupies 12 wells of the plate. And what is contained within the experimental pattern would be two recordings. So this would be trap 1 and trap 2. These are the equivalent of the patch pipette. So internal solution would be loaded into the wells that correspond to the trap wells. And then within the inlet would be the cell suspension, where we'll be drawing the cells that are actually pulled on by lateral trapping onto the trap and taken into the whole cell recording configuration. And this inlet then is continuously flowing to the outlet through the duration of the experiment. So one of the unique features of the IonFlux platform is the fact that we have continuous flow throughout the experiment. So we have a solution in the main flow channel that's continuously flowing, and then at selected times we would be adding compounds, and the compounds would be held within these 8 wells marked C1 to C8. And the timing of these can be varied and can be quite short. And then a washout period, once a compound is delivered, would start immediately upon stopping the compound delivery, due to the fact that the main flow channel is continuously flowing throughout the experiment. So this then is an experimental pattern, which again consists of 12 wells, the inlet and the outlet, the 2 traps, and then the compound wells. So the solutions for the experiment are first loaded into the plate. So the internal solutions, the cell suspension, and the compound wells are all loaded into the plate prior to loading the plate into the IonFlux reader. Once the solutions are into the plate is loaded into the reader, and then an interface is brought down which brings the recording electrodes, shown here as these gray bars, as well as the pneumatic control coming into the well. So solution delivery is going to be driven by pressure. When we pressurize a well, that solution would then be driven into the main flow channel and into the outlet. So once the plate is loaded into the instrument, the interface, the one moving part, moves down into the plate, and the gasket forms an airtight seal for the pneumatic control and brings the electrodes into the solution. Now, the other nice thing about the design of this system is since the electrodes and the fluidic control, if you will, are coming in from the top, it means the bottom of the plate is completely available. And one of the things that makes possible then is we can then bring in a heating element from underneath and do experiments at physiological temperature and control of the wells. So shown in here would be 2 traps, in this case for the ensemble recording condition. So we'd have trap 1 and trap 2. And this L shape is a small portion of the main flow channel coming from the inlet and then flowing to the outlet. And then highlighted on the left here in these colors would be the compound wells meeting the main flow channel. And since this main flow channel is continuously flowing during the experiment, these solutions are held in check and not driven out into the main channel until a compound well is pressurized. When a compound well is pressurized, that solution would be driven into the main flow channel and is being held by laminar flow against the cells that we're recording from. And so shown in this schematic would be an example of perhaps a channel, a ligand-gated channel like the GABA receptor, which would then become activated. So this would be a recording from one of the two traps as the solution is flowing past, exposing ligand to the cells. The channels open and current flows. In this case, we're showing a GABA current, a slight bit of desensitization. And then as soon as the solution stops, immediately a washout period starts. And this would be done for two recordings next to one another. This would be done across the entire plate. So once this compound, let's say it's B8 in this instance, is being delivered to the cells, this would be happening simultaneously at all 16 recordings in an IonFlux 16 or all 64 in an IonFlux HT. And since there are two recordings in each experimental pattern, it means on an IonFlux 16 we have 8 unique experiments, 8 experimental patterns, or 32 experimental patterns in an IonFlux HT. And then we can step through having 8 solutions to choose from. And one of the things that I want to present this morning is within the software, how are we defining these delivery events within our user interface. And this would be just going on, showing that we can achieve very rapid responses between or very rapid deliveries between different compound solutions. And this is in marked contrast to other versions of automated patch clamps that are currently on the market and have been for some time, where the solutions are all being held within a plate, picked up by a pipetting robot, and brought over to the recording. And so very fast solution exchanges can't be achieved because a certain amount of time has to be allocated to the physical process of picking up the compound and delivering over into the next one. And that's one of the advantages of the microfluidic approach, as well as, of course, reducing the overall costs of the system. Okay, so now what I want to do is actually step out of the presentation, and we're going to actually step into the IonFlux control software, which is shown here as the main page of the IonFlux application as it would be opened up. And what we see on this main page is that we have a table for defining the compounds that will be in our wells, as well as our recording zones. So one of the other nice features about the IonFlux approach is the fact that we can actually use just a portion of the plate if we so choose. So each zone in this case from an IonFlux HT would be making 16 recordings, 64 recordings in total. And we could choose to run just a portion of the plate instead of having to run the entire plate. And this, which is very nice for things like assay design and setup. And then shown down below would be the orientation of the wells, the traps, and then the compound wells. And what we would be defining in the table is what are the solutions that are in the compound wells, as well as notes that then might be associated with our experiment. So on the sample plate page, we would be defining simply the solution. If you will, these are the notes that would be associated with our experiment. And then we have the experimental sequence itself, which consists of a priming phase, a trapping phase. So the priming phase would be getting the solutions into position. The trapping phase is actually the patching of the cells. The break phase would be taking the cells into the whole cell recording condition. And then finally, where we'll be spending most of our time here would be the data acquisition portion of the experiment, where we would be defining the types of voltage protocols that we want to run, as well as the compound delivery scheme, and we'll go through these two features. And within all of our menus, what you see is we have sort of a drag and drop protocol builders, and I'll be highlighting what these look like. So if we had previously defined things, what we would do at the beginning of the day is then go through and say that I want to open a particular experiment that I would have defined at an earlier time and given a saved name. And for expediency this morning, we'll go through and open, say, a GABA experiment. So when I open that experiment, then my notes for the experiment are loaded into my note page. And if I save the particular set of notes, they would be highlighted here. This would be perhaps the next day, so I might want to edit this. Within the compound editor, we can change the names, but we can also simply choose to import from something that we've defined in Excel earlier. As well, we could choose to export this particular table, which we might want to do to have a template for editing the contents of this table. So, so we can simply import the updated table, if you will, for days run. Then within the experimental sequence now, my tiles are populated. And so we see during the priming phase now we have some information here. And so what is that information? And what we're defining, since we have microfluidic devices, what we're defining are really the pressures that are being applied. And here we have the traps, the main flow channel, the compound wells, for both the traps and the compound wells. So this would be a special item that's unique to the priming phase, which is simply designed to apply positive pressure to both the traps and the compounds. So much as one would do on a manual setup, one would be applying positive pressure as the pipette is being brought into solution. Just so on the IonFlux, we would be applying positive pressure to the traps. So during this priming phase, we're not pulling any cells onto our traps, or more importantly, pulling any compounds that might be flowing past into the recording trap. So positive pressure would be kept right up until we want to patch the cells, at which point we would be going from holding positive pressure to vacuum to draw cells onto the trap and make our whole cell recordings. So to define these pressure settings, then we would simply open the dialog and highlight the features. And as we can simply add things or subtract them. So if I've built previous things, I could say, oh, okay, that's something I want to change. And when each of these items is then highlighted, the parameters for that period, in this case, this would be my traps and my compounds flowing, which is shown here, or my main flow channel. So both of these would be flowing at the same time, and I can define different sorts of variables for each. And so as I highlight these features, the parameters, the pressure value, and the duration of the application is being set, and likewise with the main flow channel. So during the priming phase, it's to get the solutions into place, and at the same time, we would be running a voltage command. The purpose of the voltage command at this stage is simply to estimate the resistance of the trap. During the trapping phase, what we're doing is actually toggling back and forth between the pressure being applied or no pressure being applied. At the same time, then, we would have defined a vacuum which is being applied to the trap, and then this punctuated flow. And the purpose for this is when we stop, or when we reduce the pressure to 0 in the main flow channel, this is going to stop the flow and essentially allow the cells to be pulled onto the traps. And so during this phase, we would be punctuating the flow, which is shown here, and we can create any pattern we want, as complicated or as simple as we want. And so in this case, we just have a simple dwell that's being applied for vacuum. And then within the main flow channel, we have a somewhat more complicated pattern where we have dwell periods on the front and back end, and then pulses being applied. And for our pulses, then we give them baseline and pulse values, as well as the number of repetitions that we want to apply. And like I said, we can choose to make this design even more complicated with ramps or series features. trapping the cells, for establishing our whole cell recording conditions. And we're using conventional whole cell recording conditions. We'll be breaking into the cells using positive pressure, which is being shown in this test pulse, where we're holding the cells in place, applying a bit of extra vacuum, in this case, to take the cells into the whole cell recording condition. So one of the advantages of using conventional whole cell is that it allows for a much faster experiment. So instead of waiting for detergent to chew holes into the cell, we pop them open by pressure, which gets us into our recording configuration much faster. And this prime, trap, and break phase might take on the order of 3 to 4 minutes, depending on how long we define each period, but it's very commonly in the time range of 3 to 4 minutes for getting then to the data acquisition phase, the business end of the experiment. So within the data acquisition phase, we would be also applying pressures, in this case, to our traps, and simply dwell. So we're going to be continuously holding a bit of vacuum on these cells through the duration of the experiment. And then in the main flow channel, we again just have a long dwell period. In this case, it's about 10 minutes long, and we can define it much longer periods if we choose. So here we see this is relatively simple. So in the data acquisition phase, though, the business end of the experiment is really what's going on with our compound applications. And then we would open our compound editor and define a set of compound applications. And so what we're seeing here would be the 8 compound wells, C1 to C8, and then an application scheme. And here you can see the numbers 1, 2, and being repeated throughout. And that 1 and 2 means this is the first application of compound 1, the second application of compound 1. And if I added additional applications, so for instance, if I wanted to add a new application, I would simply highlight that, and then that's going to be an additional C1 application, which appears at the end of my table here. So for instance, let's say I wanted this to come back and repeat a C1 application at the end of my experiment. I might say, okay, at 500 milliseconds, do a 30-second long application from C1, which would then be shown here. And now, since I've made it a somewhat longer time, we see a bit of color, which corresponds to the C1 here. One of the nice things about this system is the fact that we can design these compound application schemes in any sort of variety that we want. So I can go back and continually deliver out of C1 or toggle in between and define any of these. Now, due to the fact that we have laminar flow within the main flow channel, one thing that I do need to be mindful of, and that's a real advantage to the system, is that when 2 of these compounds, if 2 of them were activated at the same time, for instance, C1 here at time 500, and then if I came along and also added C3 at this same time period, the cells would only be seeing my C3 application. And this is due to the fact that we have laminar flow in the main flow channel. And so since both of these are being applied at the same time, and the inlet for my compound number 3 actually is physically closer to the traps, to the whole cell recordings, it means that liquid is all that's going to be seen. Laminar flow dictates that liquid is all that's going to be seen by the cells. And we can use this to great advantage for systems that are complicated. So a system like the NMDA receptor, which is very sensitive to glycine and glutamate that's being released from neighboring cells, we can actually protect our recordings from that ambient material by choosing a compound well and putting clean buffer that would then protect the recording from what's going on. And this is extremely useful for systems like the NMDA receptor or the purinergic receptors, which are activated by ATP. So this is our compound editor, and at the same time that we have compounds flowing. In this case, we're defining an experiment that lasts a little less than 10 minutes. At the same time that this is running, we would also have our voltage commands running. So we're under voltage clamp conditions. And within our voltage command editor, so we have our fluidics editor, if you will, and then our voltage editor. And during this period of time, we can choose our holding potential and then the periodicity between our voltage commands. So in this case, we're applying a holding potential of minus 80 millivolts. And then we've added a period of time here. Now we can see that this period of time is a somewhat odd number, and it's actually designed to create an even period based on what's defined within the voltage command. And if we take a closer look at our voltage command editor, you can see we have this same sort of drop-down type protocol builder. And so if I wanted to add features to my voltage protocol, in this case, since this is a protocol designed for the GABA receptor, essentially we have just a holding potential being applied. And at the beginning of the sweep, we actually have a small voltage step, which we'll then be using for estimating resistance. And if I wanted to create a more complicated voltage protocol, I simply drag down and add features to my voltage protocol. And I can add any number of features. So if I wanted to do an IV plot, I would add a stack type. I can add series. And you can see again, when each of these is highlighted, then the parameters become highlighted below. When we have a dwell, we're simply defining a voltage and a period of time. When we have pulses, we have baseline values and pulse level values and periods of time associated with each of those, as well as the number of repeats. And we can add as many of these as we like. So we can create essentially very complicated voltage protocols if we choose. Here within our voltage protocol editor, we'll also be defining cursor measurements that we want to make in real time. So this first pair of cursors, which may or may not be highlighted very well. The colors are very light. I apologize for that. But this first pair of cursors would be for making estimates of resistance. And then we have a set of cursors that would be used in real time as the sweep is being run, making a delta measurement. So in this case, this would be a period prior to activation of the GABA receptor and then after. So we have our evoked current and can make a measurement in real time and build a real-time IT plot while the experiment's running. So again, we could be looking at both our sweeps as well as an accumulation of what the current amplitudes look like in real time. And then we would also be defining our sampling rate here, and our max sampling rate on the IonFlux systems is 20 kilohertz. So our voltage protocol would be running throughout the experiment. We also have the option for doing leak compensation, and particularly when one's operating in the ensemble mode. The recordings are going to have a relatively high baseline leak, and we could compensate for that at the amplifier level or choose to do it later on within the software analysis. And we also have here our additional options. So we have a high and a low gain setting, as well as then defining temperatures in this case, or turning on the whole cell series resistance compensation. So once we've defined our experimental sequence then, we would simply click on Start Experiment. So prior at the beginning of the day, then we would define what we want to do within the software, as well as physically make up our plate. And so that process, might only take, on the order of half an hour to an hour, depending on the preparation steps for making solutions in the morning and isolating cells, and then loading the experimental sequence. And with that in place, then we would say Start Experiment. Once the experiment started, we would switch over to the runtime menu. And I don't have a system hooked up to this computer that I'm presenting from this morning, but within the runtime menu, once we started the experiment, we would have the ability to stop the experiment manually by hitting the stop button here. But we also have the ability to pause the experiment, and this is one of the features that's relatively unique to the IonFlux system, where one could pause the experiment, change what's happening within the experiment, and then click on resume to continue the experiment running. During that entire time, we are continually building a set of plots, real-time plots, both for the resistance estimates, and we could choose which wells we want to look at or at all of them. So if I have it highlighted here, I'd be looking at 16 recordings for zone 1, 16 recordings for zone 2, another 16 for zone 3, and so on for all 64 recordings on the plate. As well, then, I might choose to look at my current trace, which would be a real-time IT plot. And if I wanted to look at the individual sweeps as they were being run, I would open the real-time sweeps viewer, and you can see it's telling me now that I don't actually have an experiment actively running. As well, then, I could also go in and modify what's going on at the amplifier, change the gain settings, change the wholesale capacitance compensation or series resistance correction. And so this would be what's going on at real time, and the overall progress of the experiment as it's running would be shown down in the status window here. Now, like I said, we do have the ability to pause the experiment. So if I did that, when I would go back to my setup page, and if I defined a number of different voltage commands, for instance, let's say I wanted to see, and this is particularly important during assay development process, do I prefer this holding potential over that holding potential? I could then define a number of different data acquisition protocols and save just the data acquisition phase of this experiment. And so then if I paused in real time and said, oh, that's not exactly the experiment that I want to do, I could load a different, an existing data acquisition protocol. And here's a convenient button for saving that. And that's true for each step in our protocol. So our break phase, we can choose to save just the break phase and load a particular break phase. So for instance, after working up a number of different assays, I might say, oh yeah, I want to use the trap protocol that I had defined earlier for a particular experiment, but I've already defined other features, so I might say I just want to change this break phase, and I could choose to load an existing break phase, and so on with the trap window. And then within the voltage commands also, we could choose to save just the voltage command. So for instance, if I wanted to change different voltage commands, I could pause my experiment, load a new voltage command, and then restart the experiment in the runtime. And this is particularly important, like I said, when one's defining a new assay and how you want to optimize the experiment. This pause and resume feature is very nice. So then once we've completed the experiment, what we would have is we would have a current trace plot as well as then a resistance plot for the experiment. So once I have completed something, then I would switch over to our data analysis window. And the first thing that gets highlighted is a very quick browser. So for instance, if I click on this browse button and highlighted a particular experiment, it's going to load in the details from the different phases of that experiment. So now I see what was being collected in real time during the prime phase, trapping phase, break phase, and the data acquisition phase. And here I have both my resistance estimates as well as a quick current trace. And so this would be, again, a real-time IT plot that was collected over a period of about 10 minutes. And it kind of has this strange sawtooth pattern. And as we take a closer look at this data, I'll highlight what this sawtooth pattern is coming from. So here I'm just taking a very quick look, and this browser is really designed to quickly go back and identify once I have a number of different data files. But we also have two features here, which would essentially be batch processing of this data. So for instance, I might want to actually do analysis on my real-time IT plot, in which case I could choose to take this data, which is being shown graphically, and export the numbers into Excel. And this would be a simple one-click building of a table from these highlighted values. But I also might want to take the individual sweeps that were underneath and take this entire data set, and instead of doing my data analysis within our software, simply convert all of the data to a form that can be read by other software packages. And one example of this would be the gene data software. And so to do a global conversion of the entire experiment, we have a button here for simply converting everything that was collected during the experiment in one shot. Typically, though, what we would be doing is actually going in and doing additional analysis of this particular data set. And to do that, we would be opening our current trace analyzer. And to do that, we simply highlight that, and what you see is we've had a second window open, in this case the current trace analyzer window, with a new set of buttons across the top. The first operation would be adding the data that we want to do a more detailed analysis on. And so when I click on that, it takes me to exactly where I was in the browser last time. And so I would say, okay. And the first thing you'll see is it loads the data files and tells me the data files that are being loaded. And then it says, okay, now I need to do some calculations. And the first window that we get is this current trace, or this summary of the entire experiment and these 16 recordings for the experiment. This particular set of data that I opened was run on an IonFlux 16, so there we're not seeing the zones 1, 2, 3, and 4, but rather just the zone 1. And so this is being highlighted. The difference once I'm in my current trace analyzer versus the browser is that the current trace analyzer is continually updating my current trace window here, my summary of the experiment. So if I wanted to take a closer look at the data, I would move our cursor bar in time through the experiment, and then I could say, show me my sweeps. And so these would be the 16 sweeps evoking GABA responses from our 16 recordings at this particular time in the experiment. So we can look at the sweeps, and I can define a new set of cursors. So what comes up instantly would be the set of cursors that were defined for my real-time measurement. So if I want to change those cursors, so for instance, let's say I want to take a baseline measurement during this period, and this data was being compensated in real time for leak, so all of the values are being snapped to 0. And then I want to measure my peaks here. So I might take this cursor and move it. And then I choose to make it a different type of cursor. So to start with, it was a mean, making a mean measurement. And so I'm going to make this a much broader cursor so I can add width to it. In this case, our application of GABA was approximately 3 seconds long. So I can choose to make a cursor that's 3 seconds in width. And I can say what type of data I want to extract from that. So instead of extracting a mean value, I might select the minimum value. And so now it'll be going through and catching these peaks, even if they happen at different times in the experiment. And for my baseline measurement, which is being defined here, I can say, okay, I want a somewhat broader cursor to reduce any noise, and I want that to be a mean value. And then when I say apply, my real-time window becomes updated with the new values. So, and if I change the type of measurement and apply that, you can see it's being now the entire data set is being updated in real time. Okay, so what we're seeing here are the measurements that were being made as they were being made in the experiment, and the cursors that are being shown. What we don't see is when were my liquid application periods. And so to see those periods, we could select when we turn the compounds on. So this would be the time at which the compound 1 was being turned on. In this particular experiment, compound 1 was simply buffer. So it's being applied once, twice, then compound 2 once, twice. In each case, the compound's being applied for 3 seconds. So immediately after the valve is opened, then we have the valve being closed. So these would be the times of my off events. And so we can choose to turn those, to highlight those flags. Any of the flags that are being defined here, I can then select and make measurements that are associated with those flags. So now I have a set of machine-created event flags shown here, highlighted here. I have my sweeps where I went through and defined a set of measurements. And when I say apply this template, then it will build a set of measurements, a table of measurements associated with each of my patterns. So I have pattern 1, my compound 1 addition, which happened at this time, and then we have pattern 2, 3, 4, etc. So this is how they were being seen in real time, but I might want to select how they were seen by pattern. So now I have my compound 1 application once, application twice, compound 2 application once, application twice. And so now I have a table of those measurements that were being made in real time, and if I wanted to do a more detailed analysis, I can say simply analyze these events. So these would be the events in my event table. And if I were to highlight that and say analyze events, it's going to take this data set that I've chosen with these set of event markers being defined and send them out into Excel. If I say create a new template, it takes the entire table, sends it out to Excel. So here it tells me it's exporting the data, and then I had an Excel file that was created. And so down below, I have a new sheet that was being defined. Again, we see a quick summary, the graphical summary of my measurements throughout the entire time of the experiment, as well as the traces. But then I also now have my event table. In this case, we see our current measurements getting larger, as well as the fact that we're looking at our resistances through the time of the experiment. And since I created a set of notes saying what my concentrations were, I have my concentrations listed here as well. So then I could take this data and do further analysis. We don't have time this morning, but one example would be going through then where I have an event table and doing additional functions within Excel for that analysis. So for instance, I might create a template for triaging based on current amplitude in this particular example, or resistance values. And I could then create thresholds, highlight those things. I can choose to normalize the data. I can choose to fit the data, and do that all in one quick shot as we go through the experiment. Also here, we can choose to export our real-time, our IT plot, if you will, just as we could do quickly from the browser window. Once we're in the data analysis window, we can choose to export that, or we can export particular sweeps. And when I highlight this, you'll see that it says, do you want to export what's currently selected, which would be what's being viewed here, or do I want to export an overlay window? And so what is the overlay window? So if I'm looking at a particular set of sweeps, I can choose to create an overlay window and build additional view of the data. And when I do that, then I simply say, okay, I want to build an overlay window. Now here, where do I want to start? I'm going to start over at C1, And since I've got a lot going on there, I'm going to turn that off and say I just want to look at a particular experimental pattern. And so, for instance, I might choose this experimental pattern and say, okay, I want to add that to my overlay window. And then I want to see what's it look like when GABA goes on. So that was simply buffer. This is my low concentration, a middling concentration, higher still, okay, and build an overlay. And here I have the overlay, and we can see, as we expect to see, a little bit of deviation during the baseline measurement, but not much, certainly no inward current. And then as we apply GABA, we have escalating, at escalating concentrations, we get increased peak amplitude responses and increased time of the response. And then I could choose to export this entire thing, or alternatively, within all of our windows, we can simply right-click and say, copy this image. So if I'm adding notes, I could simply add this to my notebook file. I just noticed that I'm running a bit long on time. I do apologize. There are a lot more features that are built into this system that I won't have time to highlight this morning, as well as the new features that are coming along, which I was going to highlight very briefly at the end. But instead of doing that, what I want to do is to go ahead and see if we have any questions that are out there. You can put those into the chat window. And then as well leave time for composing any additional questions that you might have. I would like to thank you for your time this morning, as well as noting the fact that we do have quite a bit of additional information, as well as very specific information about particular channel types available at our website, which is www.fluxionbio.com. Thank you very much for your time and attention.